Okay, we're going to continue with statistics. So we're going to move into inferential statistics. This is part one of inferential statistics. So when we're doing research, there are two types of numbers that we get concerned with: statistics and parameters. So statistics are numbers that represent your sample, while parameters are numbers that represent the entire population. And the goal of research is often to get your statistic to be as close to the population parameter as possible. Because if your sample is able to produce statistics that are similar to the population parameter, then that means you can make guesses about how the entire population would act, even though you only sampled a small part of that population. So something to keep in mind about parameters is that they are typically unknown because, again, it's the entire population, and so you'd have to go and talk to every single person in the population in order to actually know the parameters. So often, parameters are more of a theoretical thing. And statistics are what we is often what we know based on what we sampled from the population, and we just hope that the statistic looks like the parameter because we can't do the entire population in most cases. So let's look at these examples. I want you to think in your head if this is a statistic or a parameter. Researcher wants to know the average height of women aged 20 or older. In her sample of 45 women, the mean height is 63.9 inches. So is 63.9 inches a statistic or a parameter? It is a statistic. The researcher says in her sample, the mean height is 63.9 inches. But she's hoping that this statistic is close to the parameter. So the researcher wants to know the average height of women aged 20 or older. So she's really interested in the parameter, but the closest she can get is the statistic. Another example. A researcher wants to estimate the number of words that children know by the time they are 24 months. In his sample of 200 toddlers, the average words known is 67.3 words. Is 67.3 words a statistic or a parameter? That is a statistic because, again, it says in his sample. He's really interested in the parameter, but all he has is the statistic, and so it has to suffice. The average height for women in the U.S. is 64 inches. Is that a statistic or a parameter? That is a parameter. There is no mention of it being in a sample. So they're talking about the parameter there. Okay, so as I said, we're hoping that our sample looks like the population because then we can make guesses about the entire population even though we didn't go and sample every single person in the population. So if we look at this example, we have the population and we have the sample. And if the sample looks like this, then we can talk about the entire population even though we only have the sample. We only have data for the sample. So this is kind of the basis of what inferential statistics is using the sample to make inferences about the population. So we get our sample and then we want to infer that our results are similar to what we get in the population. So we're going to talk about how we're able to make these sort of inferences in statistics. So there are two kinds of statistics: descriptive statistics. These are just describing patterns. So in the previous video, we talked about mean, median, mode. Those are just descriptions. There was no there was no trying to make an inference to the population. Other examples are standard deviation and range. And then inferential statistics. So that's what we've been talking about. Analytic techniques that allow us to make parameter estimates based on our sample statistics. Using statistics to infer parameters. So let's talk about sampling distributions and sampling error. So let's say we took every possible sample of M&Ms. So let's talk about what that means to take every sample of M&Ms. So let's say I broke you guys into teams and gave you guys M&Ms. Then I gave each group a bunch of M&Ms. Then each group would then count how many blue M&Ms they had. Now the amount that each team has of blue M&Ms is going to change. So let's say that each team represents one sample. So again, we had multiple teams with their own sample of M&Ms. So then each team is counting up how many blue M&Ms. And yeah, so the amount of blue M&Ms is going to vary with each sample or with each team. So that idea is sampling error, the tendency of sample statistics to imperfectly reflect the population parameter of interest. So when we take samples, there's oftentimes sampling error. It doesn't get exactly what we're wanting to, it doesn't hit the parameter right on the nose. In a lot of cases it gets close, but not quite. And the sampling distribution, this is the idea that we took every possible sample, because remember we broke people into teams and gave each team a bunch of M&Ms. So if we looked at each sample, we would then have a statistic for each sample. And then once we have that statistic for each sample, we can then form a new statistic of the statistics. Let's go into what that looks like.